Welcome to Section 2.4 Detecting and Mitigating Bias. Bias in AI systems is not just a technical flaw, it's a challenge that impacts fairness, trust, and real world outcomes. If we build systems that consistently underperform for certain groups of people, those individuals experience harm and organizations face reputational, legal, and even financial risks. And now here are the objectives for this lesson. We'll be covering statistical methods for bias detection, practical techniques for remediation, real-world examples of bias in AI, and connecting these skills to exam and workplace expectations. So let's begin. So why detect bias? Bias detection begins with the recognition that AI systems are only as good as the data and processes that shape them. A system can appear accurate on paper but still be deeply unfair in practice. For example, imagine a hiring algorithm that performs well overall but systematically screens out qualified applicants from one demographic group. Without detecting that imbalance, the organization risks reinforcing discrimination. Detecting bias protects fairness, preserves accuracy across groups, and prevents legal or reputational consequences. In short, bias detection isn't optional, it's a safeguard for trust, compliance, and equity. Statistical detection methods. Statistical methods are essential for making bias measurable. The first step is disaggregating metrics. Instead of only measuring overall accuracy, we break results down by subgroups such as gender, age, ethnicity, or geographic location. Once disaggregated, we compare error rates across these groups. If one group consistently has higher false positives or false negatives, bias is likely present. We then apply fairness metrics, and demographic parity measures whether outcomes are evenly distributed across groups. Equalized odds ask whether groups have similar error rates when controlling for the true outcome. These tools make bias visible, allowing organizations to quantify disparities instead of relying on assumptions. So, practical remediation. Once bias is detected, the next challenge is mitigation. Several practical strategies exist. Relabeling addresses inconsistent or inaccurate labels in the dataset, ensuring that the ground truth is reliable. Reweighing assigns greater importance to underrepresented samples, preventing the model from being overly influenced by the majority group. The most powerful strategy, however, is expanding dataset diversity. By collecting data from a wide range of populations, environments, and conditions, we reduce blind spots that cause biased outcomes. These methods are often combined to create systems that are more balanced, accurate, and inclusive. Real world examples. Another clear example of bias appears in voice recognition systems. Early versions of digital assistants like Siri or Alexa worked reasonably well for standard, widely represented accents, but struggled with regional or non-native accents. Users often had to repeat themselves or found commands misinterpreted. This wasn't because the algorithms were weak. It was because training data heavily favored a limited range of speech patterns. The fix involved diversifying the speech datasets, collecting samples from different regions, dialects, and speaking speeds. As datasets expanded, performance improved for everyone. This example reinforces that bias detection and mitigation often come down to asking who is missing from our data and then correcting for those gaps. And now this concludes section 2.4 on detecting and mitigating bias. You've now seen how bias can be identified using statistical methods, how it can be addressed through remediation, and how real-world failures underline the need for inclusive design. Thank you.